with the chapter on real forms and involutions. So our aim was to construct a bijection between the set of real forms up to conjugation, to isomorphism, and conjugacy classes of involutions. And basically how we're going to do that is to each real form we will associate an involution. We know that real forms are in one-to-one correspondence with real structures, and two real forms are isomorphic if the real structures are conjugate. And thus, we will transform these real structures in some sense into involutions, right? So we proved that given a complex semisimple algebra, there always exists a compact real form. And we proved that if we have an automorphism of G, which is positive definite with respect to this fixed real form, then we have this, in some sense, exponential map of our automorphism, which is not the Lie group or the algebra exponential, but constructed in another way, which we could do for any positive definite endomorphism of a vector space, even anti-endomorphism of a vector space. And we have proven that this was an interior automorphism of G, and same for and same for automorphisms. For anti-automorphisms. Right. So our aim today is to construct, well, also we have proven, I think, that if sigma is a real structure, then sigma tau squared is a positive definite automorphism, and if theta is an involution, then theta tau squared is also a positive definite automorphism. Okay, so I think this was mainly what we have already proven, and our aim today is that is to prove following, that if two compact real structures commute, they are equal. And the following also for any real structure or involution there is an element in its conjugacy class which commutes with our fixed compact real structure. I don't know if we have enough time. We will construct the isomorphism, well, the bijection between conjugacy classes of involutions and conjugacy classes of real structures. Right. So we will start with the first thing, which is proposition. So let sigma and tau be compact real structures. And we claim that sigma tau equals tau sigma, then sigma is equal to tau, right? So to prove this, it will be enough to check that when restricted to the fixed points of sigma, tau is just identity, right? Because the fixed point of sigma are a real form of our semisimple algebra, of our complex semisimple algebra, and so it will be enough to prove it here to send it to the whole space by linearity. So how do we do that? So we know that if we construct this involution sigma tau, which is an involution because sigma and tau commute and they are both real structures, then we will show that this, when restricted to the fixed points of sigma, is the identity in the fixed points of sigma, right? Thus, sigma is tau minus 1, which is tau. Okay, but we know that this theta leaves fixed sigma invariant. And thus it makes sense, right, to check this. So now, theta is an involution, so we can decompose our space, fixed sigma, into fixed sigma plus fixed sigma minus, where fixed sigma plus minus are the eigenspaces for theta corresponding to plus or minus 1, respectively. Okay. So what we are saying that when we say that sigma equals tau is that we have to check that this fixed sigma minus is the zero subspace, right? I mean, theta is sigma tau, which is tau sigma. So when we apply it to an element in fixed sigma, this is just applying tau to it. So what we're saying is that there's no element here which tau doesn't leave fixed. And how do we do this? So, oops, sorry. Suppose that we have a non-zero vector here. Then we have the following. I mean, h sigma of xx, this is just minus the killing form of xx, where recall that h sigma is minus b something sigma of something. So since x is a fixed point for sigma, we have that this is just minus a killing form, and thus this is greater than 0. And we know, since tau is a compact real form, that tau is a compact real structure, that this has to be greater than 0, because this is an inner product. But now we can write h tau of xx is minus b of x tau of x, that this is minus b of x sigma tau of x, because x is a fixed point for sigma. Oops. Okay. So now notice that this is just minus b of x, comma, theta of x, but theta of x is minus x, so this is the killing form of x comma x. And this is y is greater than 0, so we have that the killing form of x comma x is both greater and lesser than 0. So we have that sigma equals tau. Okay. So we know that if we have two compact real forms which commute, then they must be the same. And what we want to prove now is the following, which in particular proves that there's only one conjugacy class of compact real structures, which is this proposition here. If sigma is a real structure on G, sorry, there exists an inner automorphism such that alpha sigma alpha minus 1 commutes with tau. Okay. Furthermore, alpha can be taken to be this phi to the minus 1/4, where phi is just sigma tau squared. Okay. So we know that this sigma tau squared by a previous proposition is a positive definite inner automorphism. I think this was this, right? So this sigma tau squared is an inner automorphism. So it makes sense to exponentiate it. And we will show that by choosing an adequate exponent there, this makes that sigma tau commute, right? Okay, why is this? So let phi equal sigma tau squared. Then we have the following. So phi minus 1 is just tau sigma squared, right? But this is oops, sorry, maybe I was mistaken here. This is tau theta okay, so tau sigma, right? Okay, I think it should be all right. But now, if we can add here a tau squared, and the resulting thing is that this is tau, sorry, sigma tau squared tau, which this is tau phi tau. Okay, so we have this, and this implies that by the properties of this exponential, that phi to the minus t is just tau phi to the t tau. And also we have the following, which is that we conjugate this by sigma tau this is just sigma tau to a third tau sigma, which this is just phi again, right? Okay, and thus phi commutes well, in fact, phi to the t commutes with sigma tau. Okay, we have these two properties, and the thing is that we want to prove that for certain alpha of the form oops, seems like I moved something around here. We want to see that for some certain value of t, which is in particular minus 1/4, conjugating that by this phi to t makes sigma commute with tau. So we just write it here. Alpha sigma, alpha minus 1 of tau. This is just taking phi to t. Well, this looks much clearer now. Phi to minus c tau. But now phi to minus c tau, we know that phi to minus c is tau phi to t tau. So this is phi to t sigma tau phi to t tau squared, which is the identity. And this, we know that phi to t commutes with sigma tau. So this is phi to t sigma tau. And similarly, if we write the other condition here, the other multiplication in reverse order, we have that this is tau phi to t sigma phi to minus t, and now we use that phi to minus c is just phi to t is tau phi to minus c tau and that phi to the t and sigma tau commute, and thus set phi to minus t and tau sigma commute. So this is identity again, and here we have phi to the minus 2t sigma tau to the minus 1. Sorry?
I got lost in this second quality.
Why? What are you saying?
No, I don't know what you have. I don't know.
Sorry, Alberto, I can't hear you well.
Can you hear me now?
Yeah,
Yeah.
but
So
you're really low on volume here.
uh, I cannot. I don't understand the second equality in that line.
The second what?
It's in the second equality in second
Yeah,
line.
this one?
Yeah, you have just substitute.
Yeah, I have just substituted.
Okay. Now I see it. Okay, perfect. Sorry, thank you.
And this is because phi to t equals tau phi to minus d tau. Okay, so well, this commutes if and only if both expressions are equal, right? So moving phi to minus c minus 2t or sigma tau to the other side, and conversely, this coincides if and only if phi to the 4t equals sigma tau squared, sorry, sigma tau to minus 2, which is just phi to minus 1. So this happens if and only if t equals minus 1/4, right? So for t equals minus 1/4, we have an element in the conjugacy class of sigma which commutes with tau. So we have two corollaries. The first one says that given a complex structure, sigma, there exists a compact, sorry, not complex structure, real structure. There exists a compact real structure commuting with sigma. And this is just because if we have that alpha sigma alpha minus 1 tau equals tau alpha sigma alpha minus 1, we multiply both on the left by alpha minus 1 and on the right by alpha. So this is alpha minus 1 tau alpha sigma alpha minus 1 alpha. This is identity, this is identity, and then we bracket like this. So alpha minus 1 tau alpha is a compact real structure commuting with sigma. And corollary 2 is the following. That any complex semisimple Lie algebra admits a unique compact structure. This is because by the previous proposition, we have that there is an element, well, if tau 1 and tau 2 are compact real structures, then there exists an alpha such that alpha tau 1 alpha minus 1 commutes with tau 2, but we have proven that if two compact real structures commute, then they must coincide. So tau 2 is equal to alpha tau alpha minus 1. And I would like to make here a small comment, which is the following. Remark. Which will be useful later on. Let sigma and tau be real structures, and phi equal phi tau squared. Suppose that we have an automorphism such that an automorphism phi such that it commutes with sigma and tau. Then we have the following, that sigma tau squared psi minus 1 equals sigma tau squared, and thus we have that phi 2 phi 2t commutes with is equal to phi 2t psi. So it commutes with this exponential that we have defined in the proof early on. So psi commutes with alpha in the previous proposition. Also, this is true. The proof is almost identical. I will upload it to Alberto's page, I think, nevertheless. But this is, and the proof is completely identical if we consider an involution here of G. We can also find an inner automorphism such that by conjugating this involution by it, we get something that commutes with tau. And we have the same corollary here, that given an involution, we can always construct a compact trivial structure commuting with it. Okay, so I think now we are conditioned to prove the big theorem. I'm not mistaken. So sorry about what I've said on the previous lectures. It seems like there was some mistake on how, well, I don't think it's a mistake. It's probably something that it's not explained, and I don't know why this is true. Onishchik defines the map between conjugacy classes of anti-involutions and involution, or real structures and involutions, by taking here a real structure sigma prime which commutes with a fixed real structure tau. But I don't know, Onishchik made some claim in the proof of the theorem proving that this was well defined that I was not sure about, and at least I wasn't sure on how to prove it. So we will proceed in a different way, which is, sorry, here we have sigma, a real structure. We will take tau, a compact real structure, commuting with sigma, which we know that there exists at least one, and thus this is an involution. And we defined, sorry, this map capital theta from conjugacy classes of real structures by inner automorphisms. This inner here, as it will be seen in the proof, I think it's completely redundant. And this will take our real structures into conjugacy classes of involutions. By inner automorphisms also. And this map will take the class of sigma and take it to class of sigma tau. Okay, so we have here the big theorem of the chapter. It says that theta is well defined bijection. So we have to prove the following, which is that this does not depend on the choice of tau, that this does not depend on the choice of sigma, because these are the both elections that we have made to define this map, that theta is surjective. Sorry, I will enumerate this. And finally, that it is injective, right? Okay. So we will start with number one, which is that it does not depend on the choice of tau. So basically, suppose that tau1 and tau2 are compact real structures commuting with sigma, as they are compact real structures, they must be conjugated by an inner automorphism. And we can write tau2 equals alpha tau1 alpha minus 1, or alpha equals, I think it's, let me check here, probably tau1 tau2 squared to the minus 1/4. Okay, and this is an inner automorphism. So we have this, and also sigma commutes with tau1 and tau2, and by the remark that I've mentioned earlier, it also commutes with alpha. Okay, but now we have the following, which is that sigma tau2, just sigma alpha tau1 alpha minus 1, and sigma commutes with this, so this is alpha sigma tau1 minus 1, and thus we have that sigma tau1 it's equal to sigma tau2. Thus it not depend on the choice of compact real structure. Second thing that we have to see is that it does not depend on the choice of a representative on the conjugacy class, and this will prove that capital theta is well defined. So how do we do this? Suppose that we have sigma 2 equals alpha sigma 1 alpha minus 1 for some alpha inner automorphism. Then we have the following, that sigma 2, alpha tau alpha minus 1, this is alpha sigma 1 alpha minus 1 alpha tau alpha minus 1, this is identity, and sigma 1 commutes with tau. And well, or maybe I should put here tau1. Where tau1 is a compact real structure commuting with sigma 1. And here we have that this is alpha sigma 1 tau alpha minus 1. So what we have to see is that this commutes with sigma 2, right? If we see that this commutes with sigma 2, then we have that the image of sigma 2 and the image of sigma 1 must be the same. And why does this commute with sigma 2? Because sigma 1 tau equals tau sigma 1, tau 1 sigma 1. And this is equivalent to saying that alpha minus 1 sigma 1 sigma 2 alpha tau 1 equals tau 1 alpha minus 1 sigma 2 alpha. And just by multiplying both sides, by alpha on the right and alpha minus 1 on the left, we get that alpha minus 1 alpha sigma 2 alpha tau 1 alpha minus 1 equals alpha minus 1, alpha tau alpha minus 1 sigma 2 alpha minus 1. And this is a compact real structure. Because tau 1 was a compact real structure, and conjugate to compact real structures are compact real structures. Right, so our map does not depend on the choice of tau, does not depend on the choice of sigma, so it's well fine. And now we see that this is injective. So how do we, we will see first that it is surjective. So if this is an automorphism, an involution, we know that we can choose a compact real structure such that theta tau equals tau theta, and thus theta tau is an involution. Just by taking squares and saying that it's the identity because it commutes, and it is antilinear because tau is antilinear and theta is linear. Okay, so theta tau, it's an involution. Theta tau commutes with tau. This is because theta commutes with tau, so it's immediate, and tau commutes with itself. And thus, since it is an involution, commutes with tau, we have that the big theta of the class of theta tau is the class of theta tau squared, which is just the class of theta. Okay, so if they give us an involution, we can construct sorry, this is not an involution, this is a real structure here. And lastly, but this is probably the more difficult part, fourth, we want to see that big theta is injective. So let sigma 1 and sigma 2 be real structures, and let tau 1 and tau 2 be compact real structures commuting with sigma 1 and sigma 2 respectively. And what are we saying? That if sigma 1 tau 1 want to see that sigma 1 tau 1 equals sigma 2 tau 2, then the class of sigma 1 is the class of sigma 2, right? So how do we do this? What does the first thing mean? The first thing means that, sorry, sigma 1 tau equals beta sigma 2 tau 2 beta minus 1 for some beta, an interior automorphism. But now tau 1 and tau 2 are compact real forms. Thus, there exists alpha, which is tau 2 tau 1 squared to the minus 1/4, such that tau 2, I think, is alpha tau 1 alpha to the minus 1. And now one has that theta of the class of sigma 1 equals theta of the class of alpha sigma 1 alpha minus 1. We just conjugate sigma 1 by this conjugation, which makes alpha 1, tau 1 and tau 2 the same. And this is just alpha sigma 1 alpha minus 1 alpha tau 1 alpha minus 1, which this is alpha sigma 1 alpha minus 1 tau 2, right? Because tau 2 must commute with alpha sigma 1 alpha minus 1. Okay. If you want to think it the other way around, this is because this is sigma 1 tau 1, and this is the same conjugacy class as taking a conjugation by alpha and then putting this here inside, which is the identity. So, okay, we can choose a representative in the class of sigma 1. Commuting with tau 2, right? So, without loss of generality, we can assume that tau 1 and tau 2 are the same, which I will denote tau in the rest of the proof. This is just because if sigma 1 does not commute with tau 2, and thus we cannot take tau 2 as a representative, as a compact real form commuting with it, we can take another representative in its class such that it commutes with tau 2. Okay, so now we suppose that we have a tau which commutes with both sigma 1 and sigma 2. But now we know that following. Sorry, let me check here my notes for a second. Okay, so tau commutes with sigma 1 and sigma 2. And notice that here in the beginning we had this beta conjugating the corresponding automorphisms. So consider this compact real form. And we have the following: since both tau and beta minus 1 are compact real forms, then there exists a gamma, which is, I don't know, right now, I think it's something like this. It might be the other way around by changing this to here, but one or the other, such that gamma tau gamma minus 1 equals beta tau beta minus 1, and gamma commutes with any automorphism commuting with beta and with tau and beta tau beta minus 1. Okay, so now consider sigma 1 tau. We know that this commutes with tau. Because sigma 1 commutes with tau, and tau commutes with tau, and it also commutes with beta tau beta minus 1. This is because sigma 1 tau beta minus 1 is equal to beta sigma 2 tau beta minus 1 beta tau beta minus 1. This is the identity. Tau squared is identity. So this is beta sigma 2 beta minus 1. And we continue here. We put beta tau squared thing. Sorry, no. We leave the tau squared here, and we now use that tau commutes with sigma 2 to pass one to the other side. This is beta tau sigma 2 tau beta minus 1, but this is beta tau beta minus 1 beta sigma 2 tau beta minus 1, which is beta tau beta minus 1 sigma 1 tau. My hypothesis, right? Okay, so this was a little bit of a mess, but now since sigma 1 tau commutes with both tau and beta tau, beta minus 1, sigma 1 tau, commutes with gamma. But now we have the following. Sigma 2 is just sigma 2 tau squared, which this is beta sigma 1 tau, beta minus 1 tau. But now beta minus 1 tau, we know that, sorry, tau beta minus 1, we know that this is tau sigma minus 1. Oh, sorry. Okay. So we have this. Wait a second. Gamma tau gamma minus 1 equals beta tau beta minus 1. So beta minus 1 gamma tau. Beta minus 1, is this right? Is this what I want here? Maybe. So what we have now, beta sigma 1 tau, sorry, beta minus 1 gamma tau gamma minus 1. Maybe. Probably this is not what I was trying to do. I mean, we ultimately have to end up with this beta gamma sigma 1 tau, sorry, sigma 1 beta gamma to minus 1. So how to arrive here? This is beta gamma sigma 1 gamma minus 1 beta minus 1. And this is sorry by this inconvenience. I just think I messed up my something like this, maybe. Does anyone have any ideas on how to prove this? It should be something like this. Okay. So we have to prove that gamma tau 1 minus 1 2 minus 1 equals 2 minus 1 tau. Oh, but
Yes, it seems that this is difficult.
yeah, but maybe I was mistaken here and I had to take, let me check on the notes, but probably I had to take something the other way around, conjugating the other way around.
Yes, because this looks like beta is an involution also. Now I'm a bit lost. No, it's not.
No, it's not. Okay, so here I made a mistake.
Ah, okay. Now I think it.
I had to put it like
I
this,
think
right?
it's right. Yeah.
Yeah,
Because now, yeah.
and here I guess this also works out. Well, let me check, but okay. Yeah, I think this should solve everything, but just tau beta. What is this? This is oops. Should be something like this, right? Okay. I think I lost my trail here. So sigma 1 tau should be beta minus 1 sigma 2 tau beta minus 1 tau beta, and this is identity, and then we have that this is beta minus 1 sigma 2 tau beta. Well, I don't know, something like that. I must have made a mistake when computing this, but when copying this, but they should commute, I think. I don't know where I made a mistake putting the minus sign, but nevertheless, it should. I will correct this on notes, but yeah. So basically, this is the same as saying that beta minus 1 tau beta is equal to gamma tau gamma minus 1, which is what we wanted to prove. Thus, if we have an automorphism which conjugates the classes of the corresponding involutions, just by taking an adequate automorphism, we can also conjugate the previous, or the real structures that they came from. So sigma 2, the class of sigma 2 is the class of sigma 1, and thus big theta is an injective. Sorry, I got a little bit lost here. I will try to fix this on the notes, but sorry. This concludes the proof. Here we have some quick examples. For example, if tau is a compact real structure, the corresponding class of involutions is just the class of identity. For example, if sigma is the split real structure, with respect to a canonical set of generators, then big theta of sigma is the class of the corresponding wave involution. And also, for example, there is this table. We knew that this is a compact real structure on SLNC, and the following real structures commute with it. And that's the corresponding involutions are the following. The class of sigma tau, where sigma tau of x is just minus x transpose. If we take the real structure just conjugation, if we take this real structure where m equals 2n and Sm was this matrix, we have the following, that theta, well, I will just write sigma tau of x, right? Because then it's just taking its conjugacy class. This is just minus Sm x transpose Sm minus 1, just the adjoint representation of Sm acting on minus x transpose. Finally, if we have this real structure, the corresponding involution will be just the identity of PQ x transpose, sorry, x identity of PQ. Well, remember that IPQ was P1s and Q minus 1s. Okay, and then we have the last example, which was that we had G complex semi-simple the algebra, and we saw that we can see, sorry, the realification of G which is isomorphic to the real form associated with this real structure, where tau is a compact real structure of G. Okay, so this is a compact real structure on G. It's immediate to see that tau times tau is a compact real structure of G plus G. Oh, sorry, this is in G plus G. Tau times tau is a compact real. Oh, sorry. It's a compact real structure of G plus G, and thus, sorry, it also commutes with sigma, and thus sigma tau plus tau, which is just taking x, y to y, x is the corresponding involution. And I think this should be all in this chapter.